Next, the radiographer must review those factors that may result in a histogram analysis error. Exposure field recognition errors, proper collimation, excessive scatter radiation, processing under the correct menu, and proper technical factor selection must be considered. Finally, the radiographer must evaluate proper positioning and tube part receptor alignment. The importance of these factors does not change with digital systems. Quality assurance and quality control. Digital imaging quality control focuses on the display monitors and viewing environment. The American Association of Physicists in Medicine published an online report number OR-03, to provide guidelines for proper performance of display devices intended for medical use. This report presents 26 test patterns that can be used to assess display device performance. The following are a few additional notes of consideration regarding quality assurance and quality control. First, those using CR systems should create a maintenance schedule for the plates. The plates should be cleaned and inspected every 3 months or as needed based on workload and conditions, using approved cleaning products only. The plates should also be erased every 48 hours if unused. Furthermore, for all digital systems within a facility, identical processing codes should be used to ensure the consistency of image appearance. Finally, the radiographer should realize that when a digital image is printed to film, the dynamic range is sacrificed and film used for this purpose is very sensitive to heat and moisture, much more so than analog film. Picture Archiving and Communication Systems. The Picture Archiving and Communication System, or PACS, is an integral part of the digital radiology imaging department. A picture archiving and communication system can generally be divided into acquisition, imaging modalities, display, viewing and workstations, and storage, archive server. Storage systems. Storage, in particular, is an ever-increasing challenge because of the increased use of multi-slice modalities, CT, MRI, ultrasound, and the increasing detail of all digital modalities. With increasing size and number of examination files comes an increased demand for storage. For example, the average size of a digital radiography study is 35 megabytes. Each of these major systems of a picture archiving and communication system is discussed here, as are trends and challenges. Picture archiving communication system is an electronic network for communication between the image acquisition modalities, display stations, and storage. For these different systems to communicate with each other, a common language is necessary. The Digital Imaging and Communications in Medicine standard was first formulated in 1983 for this purpose. And has been refined over time. This standard allows for the exchange of medical images and information among modalities, display stations, and storage. With the introduction of a common language, equipment has been designed and manufactured to be digital imaging and communications in medicine compatible as well. As previously mentioned, many modalities have been digital for some time. CT, MRI, nuclear medicine, and ultrasound all acquire images in digital format. Radiography is the latecomer to this digital environment. The process of digital acquisition for radiography has already been discussed. The digital format is necessary for radiography to be integrated as a part of the PAC, of the Picture Archiving and Communication System. The role of the Picture Archiving Communication System is to allow for the display and storage of these medical images. Now that this information is in digital form, and digital imaging and communications in medicine allows for it to be transferred to a display and storage medium, Radiography can occur in an environment that is completely digital. The patient's medical information and imaging studies can be viewed and stored as an electronic file. Through teleradiology, image files can be accessed from various workstations located throughout the facility or even by clients outside the facility if they are given access to the system. The radiologist, operating room staff, and emergency department staff can access image files at the same time if needed. For example, this system allows an ordering physician to log into the network from his or her office outside of the facility and view a patient's radiographic images without printing films or burning and sending over a CD. In addition to the images, information management systems such as Radiology Information System serve to handle textual and other information portions stored on the Picture Archive and Communication System. All such systems are networked on the Picture Archiving and Communication System so that information and images are integrated and can be retrieved from any number of locations. A display station is simply a desktop computer that allows for the retrieval and viewing of medical images from one of the modalities or storage components of the Picture Archive and Communication System. The quality and function of one of these stations depends on the user. The quality of the display monitor and the complexity of the software are major variables. A 1 megapixel or 1280 by 1024 pixel monitor is sufficient for general viewing by non-interpreting physicians and other healthcare workers, whereas a 2 megapixel 1600 by 1200 pixel monitor is necessary for general interpretation by the radiologist or viewing for quality control by the technologist. A 5 megapixel 2048 by 2560 pixel monitor is necessary for interpretation of digital mammograms. The software loaded to each display station also depends on the user. For general viewing by non-interpreting physicians and other healthcare workers, a very basic package allowing minimum adjustment may be all that is available. Quality control display stations and reading stations have greater function and capability such as more advanced image manipulation, windowing and leveling, annotation, patient demographic information, cropping, and magnification. Zoom. Even among technologists, each may have access to different functions protected by login and password to limit which aspects of a medical image may be changed, and by whom, so as to prevent accidentally damaging or negatively altering the record. As previously mentioned, one of the biggest challenges of a picture archiving and communication system is storage. With increasingly complex modalities feeding large image files into the system, the demand for storage is ever increasing. Current research indicates that 10 terabytes of storage will be needed annually per 225,000 radiologic procedures performed. The archiving component of Picture Archiving and Communication System is composed of the image manager and image storage. The image manager is the component that handles the workflow of the system moving images back and forth between viewing stations and storage. The storage component is that portion that archives the data on a storage medium, such as a magnetic tape or optical disc. Storage is usually classified as online, which is data are stored on magnetic hard drives with access times in milliseconds and transfer times in the range of tens and hundreds of megabytes per second. Nearline, a tape or jukebox uses robotic arms to retrieve the tapes automatically and insert them into a drive to read or write data. This type can access data within 60 seconds and is able to transfer data at a few megabytes per second. Offline. A removable tape or optical media is stored on a shelf in a catalog and is retrieved manually. The online storage component is networked to the picture archiving and communication system via direct attached storage, network attached storage, or storage area network. The direct attached storage has hard drives directly on the server. The network attached storage is a freestanding storage attached to the network. A storage area network is a dedicated network for connecting the storage devices to computers. Network to the picture archiving communication system. Magnetic tape is the oldest storage technology and is a linear storage medium. That is, a ferromagnetic material is bonded to a length of plastic tape. As the medium is passed by an electromagnet, it is modulated, or varied, by an electronic signal and magnetizes the medium accordingly. In a read mode, an electric field is induced in the electromagnet by the moving magnetic field of the tape. Optical disc is the other common storage technology. An optical disc, or a compact disc, a CD, has a reflective surface layer followed by a photosensitive layer that is burned by light from a laser, creating a series of light and dark spots on the disc modulated by the data signal. Recall that the digital signal is a series of ones and zeros. The light spots represent ones and the dark spots represent zeros. The data are recorded in a spiral from the center of the disc outward. In read mode, a laser light is aimed on the disc following the spiral, beginning at any point on it according to where the file is stored. If the laser light hits a light spot, it is reflected to the optical reader and is transmitted as a 1. If it hits a dark spot, it is transmitted as a 0. These discs may be arranged as an array and referred to as a redundant array of independent disks. The data are stored across the array to create backups and maximize efficiency of retrieval and storage. As the demand for data storage space increases, research continues for ways to store more in a smaller space. Optical disc technology improves, but the spiral can only be so tight. Ways of compressing the data files without loss of data are also being researched, but this is also self-limiting. Recently introduced potential solutions include the use of high-capacity flash drive arrays. The flash drives are available in 73 GB and 146 GB capacities. They are arranged as an array and used in much the same way as an array of optical disks. Another solution recently introduced is the holographic storage device. This technology makes use of a special recording medium and laser technology to record data throughout the depth of the medium. A holographic disk device stores data through its entire depth rather than just the surface. This approach has the potential of storing 1 terabyte per cubic centimeter. Radiographic film. Film construction. Radiographic film acquires the image and must then be chemically processed before it is visible. As a result, film serves as the medium for image acquisition, processing, and display. Several types of radiographic film are still used in medical imaging departments. Depending on the specific application, film manufacturers produce film in a variety of sizes, ranging from 20 by 25 centimeters, or 8 by 10 inches, to 35 by 43 centimeters, or 14 by 17 inches. The composition of film can be described in layers. The most important layer for creating the image is the emulsion layer. The emulsion layer is the radiation-sensitive and light-sensitive layer of the film. The emulsion of film consists of silver halide crystals suspended in gelatin. Silver halide is the material that is sensitive to radiation and light. The emulsion layer is fairly fragile and must have a layer composed of a polyester base so that the film can be handled and processed, yet remain physically strong after processing. Most film used in radiographic procedures has a blue dye or tint added to the base layer to decrease eye strain when viewed on a view box. Screen film is the most widely used radiographic film. As its name implies, it is intended to be used with one or two intensifying screens. Screen film is more sensitive to light and less sensitive to X-rays. Screen film can have either a single or double emulsion coating, sometimes referred to as duplicitized. Double emulsion film has an emulsion coating on both sides of the base. Film screen imaging typically uses double emulsion film with two intensifying screens. Single emulsion screen film with only one emulsion layer is used with a single intensifying screen. It has many uses, including duplication, subtraction, computed tomography, magnetic resonance imaging, sonography, nuclear medicine, mammography, and laser printing. Latent image information. The term latent image refers to that image that exists on film after that film has been exposed, but before it has been chemically processed. Film processing changes the latent image into a manifest image. The term manifest image refers to the image that exists on film after exposure and processing. The manifest image typically is called the radiographic image. The specific way in which the latent image is formed is not really known, but the Gurney-Mott theory of latent image formation is most widely believed to best explain the manner in which this process happens. To explain latent image formation, it is necessary to describe what happens at the molecular level in the emulsion layer of film, specifically what happens to silver halide crystals when exposed to X-rays and light. Physical imperfections in the silver halide crystals are the site of the latent image formation and are described in detail in box 12-4. Several sensitivity specks with many silver ions attracted to them become latent image centers. These latent image centers appear as radiographic density on the manifest image after processing. It is believed that for a latent image center to appear, it must contain at least 3 sensitivity specks that have at least 3 silver atoms each. With more exposure to the film, more metallic silver is visualized as radiographic density. Film characteristics. Current manufacturers of medical imaging film offer a wide variety of films. These differ not only in size and general type, but also in film speed, film contrast, exposure latitude, and spectral sensitivity. Film speed. Film speed is the degree to which the emulsion is sensitive to X-rays or light. The greater the speed of film, the more sensitive it is. Because sensitivity increases, less exposure is necessary to produce a specific density. Two primary factors, both relating to the silver halide crystals found in the emulsion layers, affect the speed of radiographic film. The first factor is the number of silver halide crystals present, and the second factor is the size of these silver halide crystals. Radiographic film manufacturers manipulate film speed by manipulating both of these factors in the production of specific speeds of radiographic film. Film contrast and film latitude. Film contrast refers to the ability of radiographic film to provide a certain level of image contrast. High contrast film accentuates more black and white areas, whereas low contrast film primarily shows shades of gray. As discussed in Chapter 9, film latitude is closely related to film contrast. The latitude of film affects the range of radiation exposures that can provide diagnostic optical densities. Films manufactured to display higher contrast have a narrow exposure latitude compared with low contrast films which have a wider exposure latitude. Spectral sensitivity. Spectral sensitivity refers to the color of light to which a particular film is most sensitive. In radiography, there are generally two categories of spectral sensitivity films: blue sensitive and green sensitive, or orthochromatic. When radiographic film is used with intensifying screens, it is important to match the spectral sensitivity of the film with the spectral emission of the screens. Spectral emission refers to the color of light produced by a particular intensifying screen. In radiography, two categories of spectral emission generally exist: blue light emitting screens and green light emitting screens. It is critical to have blue sensitive film with blue light emitting screens and green sensitive film with green light emitting screens. Spectral matching refers to correctly matching the color sensitivity of the film to the color emission of the intensifying screen. An incorrect match of film and screens based on spectral emission and sensitivity results in radiographs that display inappropriate levels of radiographic density. Intensifying screen characteristics. An intensifying screen is a device found in radiographic cassettes that contains phosphors that convert X-ray energy into light, which then exposes the radiographic film. Its purpose is to intensify the action of the X-rays and thus permit much lower X-ray exposures compared with film alone. As with radiographic film, the construction of screens can be described in layers. The phosphor layer, or active layer, is the most important screen component because it contains the phosphor material that absorbs the transmitted X-rays and converts them to visible light. The most common phosphor materials consist of chemical compounds of elements from the rare earth group of elements. Rare earth elements are those that range in atomic number from 57 to 71 on the periodic table of elements. They are referred to as rare earth elements because they are relatively difficult and expensive to extract from the earth. Intensifying screen systems used in cassettes generally include two screens. The screen that is mounted on the side of the cassette facing the X-ray tube is called the front screen, and the screen that is mounted in the opposite side is called the back screen. With two screens, the film, double emulsion, is exposed to approximately twice as much light as a single screen system because the film is exposed to light from both sides. Some screen systems use only a single screen and are used with single emulsion film. When a single screen is used, it is mounted as a back screen on the side of the cassette that is opposite from the tube side. When loading a single emulsion film into the appropriate cassette with a single screen, the emulsion side of the film must be placed against the intensifying screen. Film is much more sensitive to visible light than to X-rays. By converting each absorbed high-energy X-ray photon into thousands of visible light photons, intensifying screens amplify film optical density. Without screens, the total amount of energy to which the film is exposed consists of only X-rays. With screens, the total amount of energy to which the film is exposed is divided between X-rays and light. When intensifying screens are used, approximately 90% to 99% of the total energy to which the film is exposed is light. X-rays account for the remaining 1 to 10% of the energy. Intensifying screens operate by a process known as luminescence. Luminescence is the emission of light from the screen when stimulated by radiation. The desired type of luminescence in imaging is fluorescence. Fluorescence refers to the ability of phosphors to emit visible light only while exposed to X-rays. Screen speed. The purpose of intensifying screens is to decrease the radiation dose to the patient. Because screen phosphors can intensify the action of the X-rays by converting them to visible light, the use of screens allows the radiographer to use considerably lower mass. The advantage of using screens is the reduction in recorded detail. The disadvantage of using screens is the reduction in recorded detail. Screen manufacturers produce a variety of intensifying screens that differ in how well they intensify the action of the X-rays, and therefore differ in their capacity to produce accurate recorded detail. The capability of a screen to produce visible light is called screen speed. A faster screen produces more light than a slower screen, given the same exposure. Although very fast screens reduce patient exposure, they also degrade image resolution and increase quantum noise, so a balance must be chosen. Several factors affect how fast or slow an intensifying screen is, including absorption efficiency, conversion efficiency, thickness of the phosphor layer, and size of the phosphor crystal. The presence of a reflecting layer, an absorbing layer, or dye in the phosphor layer also affects the screen speed. Absorption efficiency refers to the screen's ability to absorb the incident X-ray photons. A rare earth phosphor screen absorbs approximately 60% of the incident photons. Conversion efficiency describes how well the screen phosphor takes these X-ray photons and converts them to visible light. Increased absorption and conversion efficiency mean that rare earth phosphors have increased speed when compared with a previously used screen phosphor. Calcium tungstate. This increased speed allows the radiographer to substantially reduce the X-ray exposure needed to produce images with the appropriate amount of density. The thickness of the phosphor layer and the size of the crystal also have an effect on screen speed. A thicker phosphor layer contains more phosphor material than a thinner phosphor layer. The phosphor is the material that converts X-rays into light. So, if more phosphor material is present in a screen, more light will be produced, increasing the screen speed. The size of the phosphor material crystals also affects screen speed. Larger phosphor crystals produce more light than smaller phosphor crystals. Again, more light being produced means that the screen is faster. The final factors that affect screen speed are the presence or absence of a reflecting layer, a light-absorbing layer, or light-absorbing dyes in the phosphor layer. A reflecting layer is used to increase screen speed by reflecting light back toward the film. A light-absorbing layer or light-absorbing dyes present in the phosphor layer are used to decrease screen speed by absorbing light that would otherwise reach and expose the film. The ability of the screen to produce visible light can also be described in terms of its relative speed. Relative speed results from comparing screen film systems based on the amount of light produced for a given exposure. Most radiology departments that use film screen technology have at least two different speeds of intensifying screen systems. A fast system usually is available with a relative speed of about 400. A 400 speed system is a good compromise between the beneficial effect of decreasing the patient dose and detrimental effect of decreasing the recorded detail. A slower system is usually available, and it is sometimes labeled on the outside of the cassette as detail or extremity. The relative speed of this system typically is 100. Detail or extremity screen systems are relatively slow and therefore require greater exposure and result in higher patient doses. However, the atomic parts imaged with detail or extremity screen systems generally are small. Therefore, they do not require large exposures. Detail or extremity screen systems produce excellent recorded detail. The radiographer must be careful in selecting the appropriate screen system for the examination ordered. Cassettes with extremity and detail screens should be used only for tabletop examinations. They should never be used in the bucky tray because of the excessive amount of exposure needed. Screen maintenance. The maintenance of intensifying screens is significant because radiographic quality depends in large part on how well the screens are continuously maintained. Two important maintenance procedures should be performed on intensifying screens. The first is regular cleaning. The outside surface of screens comes into contact with the environment and with the hands of those unloading and loading cassettes, which results in the natural oils on fingers and hands being deposited on the screen surface. These oils tend to attract dust and dirt, which can build up to the point at which they are actually imaged on radiographs as artifacts. Screen cleaning should be done routinely. The cleaning is accomplished with commercially available anti-static intensifying screen cleaner fluid and gauze pads. The second important maintenance procedure is to check cassettes for film screen contact. Good film screen contact exists when the screen or screens in direct contact with the film are in direct contact with the film. Poor film screen contact greatly degrades recorded detail and is usually seen as a localized area of unsharpness somewhere on the radiographic image. Rarely is film screen contact so poor that unsharpness can be seen across the entire radiograph. A major part of testing for film screen contact is identifying problem cassettes. The film screen contact test is easily accomplished, but it requires a special wire mesh test tool. The wire mesh test tool is placed on the cassette in question and radiographed with an appropriate technique. The resultant radiograph is then viewed from a distance of approximately 6 feet to determine any areas of unsharpness, which indicate poor recorded detail. Areas of poor contact appear darker than areas of good contact because of the increased spreading of the light photons. The remaining component in the film screen image receptor is the cassette. Serving as a container for both the intensifying screens and the film, the cassette must be light-proof, lightweight for portability, and rigid enough not to bend under a patient's weight, all while allowing maximum amount of radiation to pass through and reach the screens. Low X-ray absorbing materials such as thermoset plastic, magnesium, or even graphite carbon can be found in the front of cassettes. Inside the back of cassettes may be a thin sheet of lead foil designed to absorb backscatter before it exposes the film. Automatic film processing. The purpose of radiographic processing is to convert the latent image into a manifest image. The manifest image is the image that exists on the film after processing. According to the Gurney-Mott theory, this process is the first step toward creating a visible image on a radiographic film. Exposure of the silver bromide crystal in the film emulsion by light or X-ray photons initiates the conversion process. Chemical processing of the exposed film completes the conversion process and transforms the image into a permanent visible image. Components. An automatic film processor is a device that encompasses chemical tanks, a roller transport system, and a dryer system for the processing of radiographic film. The processing of a radiograph occurs in 4 stages: developing, fixing, washing, and drying. Each stage has its specific function and processing method. Developing. The primary function of developing is to convert the latent image into a manifest or visible image. The purpose of the developing or reducing agents is to reduce exposed silver halide to metallic silver and to add electrons to exposed silver halide. 2 chemicals are used to accomplish this purpose: phenidone and hydroquinone. Phenidone is said to be a fast reducer, producing gray or lower densities. Hydroquinone is said to be a slow reducer producing black or higher densities. Both phenidone and hydroquinone are also act to soften and swell the emulsion layers. Phenidone and hydroquinone are said to be synergistic, or to have superadditivity. Superadditivity means that together these chemicals produce a greater effect on the film than they would individually. This is used to advantage by using both chemicals in combination to develop or reduce the exposed silver halide. The developer solution needs an alkaline pH environment for the chemicals to function properly. During the development process, developer solution donates additional electrons to the sensitivity specs or electron traps in the emulsion layers of the film. These additional electrons attract more silver to these areas, thereby amplifying the amount of atomic silver at each latent image center. Exposed silver halide is reduced to metallic silver when bromide and iodide ions are removed from the emulsion. The atomic silver that was exposed to radiant energy, light and X-rays, is converted to metallic silver and presented as radiographic densities. Unexposed silver halide does not react immediately to developer because it has not been ionized and does not accept electrons from the developer. Given extended exposure to developing solution or exposure to excessively heated developing solution, however, even unexposed areas of film can react to developing solution. Exposed silver halide reacts to developer by accepting electrons because neutral atomic silver that was previously bonded to either bromide or iodide has room to accept electrons in its outermost electron shell, the O shell. Fixing. The primary functions of the fixing stage are to remove unexposed silver halide from the film and to make the remaining image permanent. There are also two secondary functions of fixing. One is to stop the development process. The other is to further harden the emulsions. Fixing solution must remove all undeveloped silver halide while not affecting the metallic silver image. The purpose of the fixing agent is to clear undeveloped silver halide from the film. A thiosulfate, sometimes also called hypo, such as ammonium thiosulfate, is the chemical used as this agent. The fixer solution needs an acidic pH environment for the chemicals to function properly. Washing. The purpose of the washing process is to remove fixing solution from the surface of the film. This is a further step in making the manifest image permanent. If not properly washed, the resulting radiograph shows a brown staining of the image, resulting in image loss and a decrease in its diagnostic value. This staining is caused by thiosulfate, which is the fixing agent, that remains in the emulsion layers. Some thiosulfate always remains within the film, but the goal of washing is to remove enough so that the radiograph can be used for an extended period. The process by which washing works is referred to as diffusion. Diffusion exposes the film to water that contains less thiosulfate than the film. Because the film contains more fixing agent than the water, the fixing agent diffuses into the water. Eventually, thiosulfate concentrations in the wash water can become greater than those in the films being processed. Therefore, the wash water must be replaced frequently. Water flows freely from the input water supply through the wash tank and down the drain while the roller transport system is operating. This type of system provides a constant supply of fresh wash water to aid in the diffusion process. The moving water also causes agitation and increases diffusion. Drying. The final process in automatic processing is drying. The purpose of drying films is to remove 85 to 90% of the moisture from the film so that it can be handled easily and stored while maintaining the quality of the diagnostic image. As a result, finished radiographs should retain 10 to 15% of their moisture when processing is complete. If films are dried excessively, the emulsion layers can crack, which decreases the diagnostic quality of the radiograph. Increased relative humidity decreases the efficiency of dryers and processors, so an increased drying temperature is necessary. Processors are equipped with thermostatic controls to allow selection of a wide range of dryer temperatures. To chemically process a radiographic image, specialized equipment and systems must perform concurrently to move the film through the processing stages according to the manufacturer's specifications. Systems. Automatic processors use a vertical transport system of rollers that advance the film through the various stages of film processing. A film is introduced into the processor on the feed tray. The feed tray is a flat metal surface with an edge on either side that permits the film to enter the processor easily and correctly aligned. Automatic processors use different types of rollers to move the film through the processor. Transport and crossover rollers ensure the film is moved into and through the tanks at a constant speed. An electric motor provides power for the roller assemblies to transport the film through the processor. The on-off switch that provides electrical power to the processor activates this motor. Most processors are also equipped with a standby control. The standby control is an electric circuit that shuts off power to the roller assemblies when the processor is not being used. Pushing the standby control switch when one is ready to process a film can reactivate the roller assemblies and water intake. Replenishment refers to the replacement of fresh chemicals after the loss of chemicals during processing, specifically developer solution and fixer solution. The replenishment of chemicals used in the automatic processor is necessary because these chemicals eventually become exhausted or inactive, and their ability to perform their function decreases. Developing solution becomes exhausted from both use and exposure to air, which reduces its chemical strength. Fixer solution becomes exhausted for several reasons. It becomes weakened from use as a result of accumulations of silver halide that are removed from the film during the fixing process, and because developer solution remains in the film, which decreases the strength and activity of the fixer solution. The amount of solution that is replenished is preset and based on the size of the film, or occurs at timed intervals. Replenishment systems usually are adjusted so that more fixer solution is replenished per film in comparison with developer solution. Automatic processors have a recirculation system for the developer and fixer tanks. Each tank has a separate system that consists of a pump and connecting tubing. The recirculation system circulates the solution in each of these tanks by pumping solution out of one portion of the tank and returning it to a different location within the same tank from which it was removed. The recirculation system keeps the chemicals mixed, which helps maintain solution activity and provides agitation of the chemicals around the film to facilitate fast processing. Circulation also helps maintain the proper temperature of the developer solution. The developer recirculation system includes an inline filter that removes impurities as the developer solution is being recirculated. Temperature control of the developer solution is important because the activity of this solution depends directly on its temperature. An increase or decrease in developer temperature can adversely affect the quality of the radiographic image. In most 90-second automatic processors, developer temperature must be maintained at 93 to 95 degrees Fahrenheit. An immersion heater is a heating coil that is immersed in the bottom of the developer and fixer tank. Most automatic processors are thermostatically controlled to heat the developer solution to its proper temperature and maintain that temperature as long as the processor is turned on. Radiographs must be properly dried to be viewed and stored. The film is dried by hot air that is blown onto both surfaces of the film as it moves through the dryer. This air is forced through the dryer by a blower and is directed onto the film by air tubes. The temperature of the air that is used to dry films is thermostatically monitored to accurately control moisture removal from the film. Inadequate processing is evidenced by certain appearances of the finished radiograph. Particular problems can be pinpointed by analyzing the radiographs. These problems and the radiographic appearances that indicate them are summarized in Table 12-3. Quality control. Unexposed film should be stored in its original packaging so that important information about the film can be maintained, such as expiration date and lot number. Film boxes should be stored vertically, not horizontally, to prevent pressure artifacts on the film. Film should be stored away from heat sources and ionizing radiation. Both heat and radiation can cause the silver halide in film emulsion to break down, which results in fogged film. The shelf life of film, as expressed by its expiration date, must be observed. Film should not be used beyond this date. How film is handled in the darkroom can have a profound effect on the radiographs. Common hazards to radiographic quality that can be found in the darkroom are white light exposure, safe light exposure, ionizing radiation exposure, and other potential hazards. Darkrooms must be free from all outside white light exposure. A white light source may be located inside the darkroom, but it should be connected to an interlock system whereby the film bin may not be opened as long as the darkroom white light source is on. In addition, the temperature and humidity can adversely affect the film. Film should be stored and handled at temperatures ranging from 55 to 75 degrees Fahrenheit, with a relative humidity of 30 to 60%. Without moisture in the air, low humidity, any buildup of static charges can expose the film. Countertops must be clean and static-free to avoid the formation of radiographic artifacts on the films. There are several brands of commercial cleaning fluids that contain an anti-static component ideal for cleaning darkroom countertops and processor feed trays. Other potential hazards to film in the darkroom include heat and chemical exposure. Film stored within the darkroom should not be near any heat source. Processing chemicals must be kept away from film and film handling areas to prevent exposure and contamination of these areas. Ionizing radiation exposure to film in the darkroom is a potential hazard because many darkrooms share common walls with radiographic rooms. The walls that are common with the darkroom and radiographic room must be lined with lead as required by law for standard protection from radiographic exposures. The film bin, where film is stored and available for immediate use, should also be lined with lead to prevent fog that may result from radiation exposure. Safe lights used in the darkroom must be equipped with a safe light filter appropriate for the type of film being handled in the darkroom. Commonly used filters include Kodak Raton 6B for blue-sensitive film and Kodak GBX for orthochromatic film, which is sensitive to both blue, violet, and green visible light. Safe light filters must be free of cracks because white light that leaks from the safe light could expose the film. The power rating of the light bulbs used in safe lights should be no greater than that recommended by film manufacturers, generally 7.5 to 15 watts, which is indicated on the outside of the box of radiographic film. Good radiographic quality cannot be achieved when film is improperly stored, mishandled before or after exposure, or incorrectly processed. Common film artifacts resulting from improper storage, darkroom handling, or improper processing are shown in Figure 12-22. A quality control program, also must be implemented and systematically followed to ensure proper processing of radiographic film. Silver recovery.